Hey everybody, we're Senior Design Team 6, otherwise known as Team Mojo Squared. My name is Josh Atkins, this is Kyson Montauk and John Shaver, and today we're going to be telling you guys about our smart home automation project that we spent the last 9 months working on. We'll begin with a technical and functional overview of how the system works, then we'll move on to discussing the engineering requirements that quantify the terms of success for our project. Then we'll give a live demo of how our system works and the different features that it has, and then we'll conclude with the unique aspects of our system, as well as some recommendations for future seniors. We hope you enjoy our presentation. Although there are other home automation and smart home solutions available on the market today, the ones that offer a diverse and powerful feature set are simply too expensive for the average consumer to choose to afford to put in their homes, and the lower cost ones simply aren't worth the investment. Our challenge was to create a home automation smart home solution that allows users to control and monitor devices within their home from any internet-connected device, from within and without. We believe that the customer should come first, which is why we've sought to provide a high-performance solution at low cost, which we put at a premium priority. But in addition to low cost, we want to provide a solution that is easy to use for a wide demographic of users. It needs to be accessible from anywhere, from any internet-connected device. The data that we're collecting about the home needs to be accurately reported on the user interface. And since data and control of the home is at stake here, we need to make sure that that data and control is transmitted securely so that homeowners won't have anything to worry about.
Now let's take a few minutes to look at our system from a high-level block perspective. At the core of each and every Mojo system is the master control unit. This device is essentially an embedded Linux board running an Apache web server that provides a way for the user to interact with the system. Also running on the master control unit is a daemon process that is responsible for controlling and updating the status of each and every device connected to the system. All of the client nodes are connected to the master control unit via an RF link provided by the RFM70 module. Taking a closer look at the node blocks near the bottom of the screen, we can see that each node is comprised of a microcontroller, an RF board for wireless communication, and other various components used to power the node and provide monitor and control functionalities. The node power supply is comprised of a transformer that steps the 120 volts AC wall signal down to a more usable 12 volt DC signal. From here, the LDO regulators are used to provide 3 and 5 volt rails for various node components. The heart of each client node is an AVR microcontroller that has been programmed using AVR GCC. The microcontroller is responsible for interfacing with all devices on the node. One of the major features of the node is to collect information about the current flow and power consumption of a connected device or appliance. This is done using an active power monitoring IC, which communicates with the microcontroller over a serial UART connection. In addition to the power monitoring IC, onboard temperature sensors are continuously monitoring the ambient temperature through the N-in signal and output the signal to the microcontroller using the temp sense line. This information, along with the power information previously mentioned, is sent to the master control unit and stored in a database for further processing.
Alright, now I'd like to discuss the engineering requirements for our project. The first two I'd like to discuss involve measurement accuracy. With data like current and temperature being sent to the user, we find that it's very important that it's accurate. So we've chosen limits of plus or minus 10% for the current and plus or minus 5 degrees Fahrenheit for the temperature. To verify that we meet these criteria, we have used equipment in the lab, and it has shown that we have passed both. The next engineering requirements I'd like to discuss involve safety. Since the device is being installed into a user's home, it is important that all hazards are removed. To do this, we've implemented both over-current protection and over-temperature protection. These requirements include the power path is opened if current reaches 10 amps, plus or minus an amp, and if temperature exceeds 140 degrees Fahrenheit. Again, using equipment in the lab, we tested both requirements, which showed passing on both.
The next 4 engineering requirements are related to the user interface. The first is that we require it to be cross-platform. Now we've chosen to develop a web-based user interface that is inherently cross-platform and accessible on Windows, Linux, Mac, iOS, as well as Android through mobile and desktop browsers. In addition, we wanted to support multiple users as well as multiple user types on the system. Multiple users are achieved through supporting different usernames and passwords that allow users to log in to a unique profile on the user interface. Multiple user levels means that each user has a configurable set of access privileges from an inherent hierarchy of control. This is reflected in the user interface by varying options in the user interface according to privilege level. Furthermore, to ensure that our user interface is easy to use for a wide demographic of users, we conducted usability testing and required that at least 90% of the test subjects were successfully able to sync a node using the UI, which was conducted during winter term and successful.
To ensure that our system is both responsive and robust, we require two things. First, we require that all nodes are able to sync to the system within 30 seconds. Second, we require that 90% of all valid requests issued to the master control unit are handled without any issues. Both of these engineering requirements have been tested through the use of automated test scripting as well as user testing, and both of them check out. So now that we've had a chance to look at these system requirements and a wide project overview, we're going to take a closer look at our system by doing a demo and then looking at some of the actual components themselves in more detail.
The first thing the user is greeted with when they access the user interface is a login page. Now, I'm going to log in as an administrative user that we've created for the purpose of this demonstration. So it remembers my password, so I'm going to log in now. And after doing that, I can see the rooms in my house, and then if I click on that, I would see the devices. After logging in, the next step to begin using our system is to add new devices. In order to do this, you need to be an administrative user and navigate to the admin page, and then click on the devices link in the list view. Now, to begin adding new devices, you click the Start Sync button in the user interface.
At this point, the master control unit goes into a state where it's starting to listen for new devices to be added to the system. So we can go over to our new devices that we have installed into our wall, and we can press the button on the platform itself, and when a solid green light indicates that the device has been successfully synced with the master control unit, and the device is also now visible within the GUI.
Now if I just click on this, we'll be able to see that it's now configurable, and I can name this outlet, because that's the device we're syncing, and add it to the Burrow device list. And now if I navigate to the devices page, click on the Burrow, if I turn the device on in the user interface, you can see the lights now turn on. So now let's take a look at a more in-depth view of how the UI works and all of its intricacies and features. The home screen is a list of the devices sorted by room. So here in the Burrow, we have a list of devices that nodes that we've synced to the system, and we'll come back to that in a second. Next, we have a statistics page here in the stats menu, and since we've just synced the system for the first time, there's not a lot of data that's really relevant to us right now. But in the long term, with the data we're logging, we'll have a lot more data that can be graphed in this page. Next is the admin page, which contains by far the most complex from the standpoint of the UI. There's a users page which allows configurable privilege levels for every single user in the system, so I can activate or deactivate monitor control privileges for different users of the system as an admin, and those are related hierarchically, so you can only control the access privileges of users with strictly less privileges than the user currently logged in. Now I can go to rooms and create new rooms. Notifications allow the user to configure whether or not they want to receive over temperature or over current detected notifications via text message. And the most interesting page probably is the sync devices page, which allows new devices to be added to the system. In the home devices page for monitoring and controlling devices within the system, we can see that the outlet has a status indicator and control toggle, as well as some relevant node information. Here depicted temperature and current power, and you can see that the power is 0 since it's currently off, and the temperature is around 31 degrees Celsius. Here on the switch it's a little warmer because it's been on recently, but I can use these to turn on the devices in the system, and we can click this button to get a more detailed power profile. And within about 5 seconds we'll start to see data about the system, and all of this is being recorded by the hardware and depicted in the UI.
Although it's not an explicit engineering requirement, we felt as a team that it was very important for our system to maintain existing control interfaces. So as you can see, we kept on the platform and the module boards, we kept the light switch that allows the user to simply turn it on and off the lights as if they had not installed the system in the first place.
Alright, now that we've looked at how the user interacts with the system, let's take a quick look into the hardware of the node. As you can see, the node is made of 2 boards, the platform and the module, and they connect like so. On the module, we have the current sensor and a temperature sensor for safety. The module also contains the power supply. Now the power supply supplies power to the rest of the module along with the platform. Now looking at the platform's main focus is the wireless side of the device. It contains the microcontroller and the RF transceiver. Together, they make up the node.
We ran into quite a few issues while we were working through the development of this project. One of the big ones that we had problems with was getting the radio RF boards to work right. And the reason for this is kind of twofold. The biggest reason was that we chose a part that has very poor documentation, and also there's not very many people use it, so there's not a very large community there to support the device. The reason that we chose the device is because it uses a high data rate, and it was also pretty cheap. But we found that the cons of this definitely outweighed all of the benefits that we saw at the beginning. So one recommendation that we'd like to make to future students and seniors working on their senior design projects is choose parts that are tried and true, that you know that you are familiar with, one, and that there's a lot of people that can help you in the community and on the internet. They can help you when you run into problems that you may not know how to solve. Another one of the major issues that we had was getting accurate current sensor measurements. We went through several revisions of our project in order to get accurate current sensor measurements. And the biggest recommendation and the biggest learning experience that we took from this was that if you're going to fail early. We failed late, and we ended up scrambling like crazy at the very end of the project to implement a accurate current sensor, whereas had we done initial testing earlier during the development cycle, we probably could have avoided this entire situation. So we were able to work out of the tough situation that we found ourselves in as a team because of 2 main things. The first was that we picked very good team members, and the second was that we had solid engineering requirements. Our team members, we chose to be, our team members have very diverse skill sets, as well as all of our team members are very self-motivated, hardworking, all those good things that you want to look for in teammates. As far as engineering requirements go, we picked engineering requirements that gave us a little bit of wiggle room on our specs, and we also chose ones that are not contingent on one another. So if we weren't able to meet the exact spec of one, it didn't impact the success of another, and that was definitely crucial in successfully completing the requirements as per the class.
So moving forward with the project, and especially Mojo Squared, we have a lot of ideas to implement new devices and add on to the devices that we already have. Moving forward with temperature sensors that can be placed in a room that is low power, along with locks and other devices, opens a lot of doors in the future for Mojo Squared.
So thank you guys for listening. We're Team Mojo Squared, or Team 6 for Senior Design. We went over the engineering requirements and a brief overview of our design. We went over a pretty thorough demo of how our project actually functions, and we made some pretty empirical recommendations for future seniors taking this class. Before we say goodbye, we'd like to send out a big thank you to Don, Kevin McGrath, Team Metro Swift from the CS department for all their support and help with our project. And until next time, take it easy.